good way to keep safe.
All right, so at the top, this is actually written above, but this is just to make it a little more clear and actually give you their sizes of, like, I don't know what you call it, like the size of what the wave actually is in real life.
A microwave.
So that first one, let me pull this out, make sure they didn't say something in my chat. No, okay.
How do you get it? Sucker?
So in that first one, the wavelength is the size of a radio wave. Radio. So the radio that you listen to in your car, in a stereo, something like that, they have very big waves. They're coming from radio towers. They are 10 to the third meters in length. So it's like, could be as big as a mountain, could be as big as this building. Those are big waves. Next one is a microwave. Okay, so microwaves that you use at home to cook with, those are also very big waves. They're about the size of a person. So if they're that big, they should just be going right over you, even if you stand right in front of it. It shouldn't be hurting you. They do worry that it hurts fetuses when a woman is pregnant. I haven't seen any proof that that's actually true, though, because it's a very big wave. I think they just say that because they just want you to be extra cautious when you're pregnant.
Big waves can't hurt you anyway.
It shouldn't hurt you. That's what I just said. Next one is an infrared wave. So infrared. I'm a little out of room in my smart board. It's called infrared. That is the size of heat waves. So this is something you can see if you have like heat wave detectors. It's like the heat that literally we give off in our bodies or anything else. It's infrared waves, so it's all heat. I'll put that down here just so you know. Heat waves are fairly big too. The next one is our visible light. So when I say visible light, what I mean is visible to us. I don't mean visible light to every animal on the planet. Some animals have very different visible spectrums than we do, but ours is right there in that size, 0.5 times 10 to the negative 6. That's about the size of bacteria. Those are the size of waves that your eyeballs can detect. Anything smaller or bigger than that, our eyes just can't see it. Next smaller down is called ultraviolet. Ultraviolet waves. Now, ultraviolet is slightly more purple, we think, because it's like basically just slightly smaller than purple. It's just slightly smaller than our eyes can see. We do have some machinery that can see ultraviolet lighting, and we do know that some like birds of prey and other types of animals can see that type of light spectrum. Further down is X-ray.
X-ray's right.
Now, basically, when I get around this size and on, this is where it's dangerous. Okay, so when I get about right after ultralight and on, if it's any smaller than those, that wave light is probably going to be very dangerous to your cells. It can corrupt your cells, can cause you to have cancer. These are ones we want to be wary of and protect ourselves from. The last one is called gamma rays. Now, gamma rays are what are produced from radioactive material. That's why they say that radioactive material is dangerous. We have to protect ourselves from those because they give off gamma rays. We also have gamma rays just naturally around us all the time, which is why you should be wearing sunscreen and things that protect your eyes, like sunglasses.
How do they know?
Because they've done a lot of studies, and people who have been around radiation more tend to get cancer and die.
That's just a trauma. And then.
It's just over time of movement. All right.
That way doctors run out of.
Yeah, they don't want to get more radiation. All right, scrolling down. So our light equations is all we have left. We're not really going to solve more than one. I'm just going to show you how to solve one. Mostly we're just going to discuss it. So on our little formula here, C is the speed of light, which is 3 times 10 to the 8. That's how fast all light travels if it has nothing blocking its path. So like in space, it's very fast. Wavelength is like this upside down Y. So anytime you see that, it means literally the length of the wave, or the smaller the wave is, the more dangerous. And then lastly, F is frequency. Frequency just means how fast the wave is going, so how many waves per second. The smaller the wave, the more waves per second. All right, so this first one, I'm gonna draw a little triangle. We've seen one of these triangles before for density. You could use it on this light calculation as well. The C would go at the top, and then F, and then that funky upside down Y is supposed to mean wavelength. So in that little triangle, when I ask you to solve these, I'm only gonna ask you to solve it a little bit. You have one practice on your slides you'll finish today. But if you want to know the wavelength of something, I would cover up the wave, and then my formula would be C divided by F equals wavelength. If I want to know frequency, well, I cover up the F, and that leaves me with C divided by wavelength. So that's how you decide, like, when do I divide, when do I multiply? You just cover up the one you're looking for, and it tells you what to do in the triangle. All right. Now, just for like showing you what should kind of happen, if the frequency of a wave is double, what should happen to the energy of the wave? So if my frequency goes up, it speeds up. What happens to the energy? If it does. So if my frequency goes up, what did you say? Goes down or up? No, it should go up. When frequency goes up, energy goes up. So they go up together. That's called a linear function. They go up together. So if I double my frequency, so if I double the frequency, like the asked you in that question, what happens if I double the frequency? Well, then I double my energy. Okay, so frequency and energy go together. The faster the wave is, the more energy it has. The smaller the wave is, the faster it would go, the more energy it would have. Then down here, and scroll down so I can see it better. You'll have it. Scroll. Dang, I don't want to erase my formula.
Wait, frequency equals to what on the?
Oh, no.
What is frequency?
I don't want that open. No. I'm going to rewrite it so we have it up here. So wave equals C over frequency, and frequency equals C over wave. All right. Now, that second one, I'm actually going to solve a practice problem just so you can see it occurring. So if frequency is doubled, my frequency is doubled, what happens to the wavelength of the wave? So if I have my frequency and I just double it down here, what happens to the wave? So I'm going to use this. I'm trying to figure out what happened to the wave. C over F. That's the formula. If I change my frequency on the bottom to something like I have wavelength equals 3.00 times 10 to the 8. That's C. That's always C. That's the speed of light. And I divide it by, let's pretend my frequency is 4. All right, let's pretend it's 2. That's what I wrote down. I don't want to recalculate. So if I pretend it's 2, then the answer would be 1.5 or 150,000,000. Try it down.
What happened?
I'm just proving a point. If you would actually listen and follow down. Now, if I double it, like this says, if the frequency gets doubled, so I'm going to double the 2. I'm going to double the frequency. I'm going to try another practice problem. C is still the same. 3 is always 3.00 times 10 to the 8. But now I want to double the frequency, like the question asked. If I double it from 2 to a 4,
Yeah, there's no room in.
then right below.
There's no room below either.
You get this side down.
The answer would be 7,500,000. Okay. Now, why I'm showing you that is just like, well, now you can think about it logically. What happens if my frequency's doubled? So from here to here, did the wavelength go up or down? I had 2 as my frequency, and then I doubled it. Did the wavelength go up or down?
Down.
Down. So when frequency goes up, then wavelength goes down. That's all you had to get from it. But if you don't see how it works mathematically, that's using the formula. I used it. I put in just practice numbers 4 and a 2. So I went from a 2 to a 4, I doubled it. It made my wavelength go down. So when frequency, the speed of the wave goes up, the size of the wave has to go down. The smaller the wave, the faster it goes. Frequency is fast. All right. So next one, I'm just going to say it. So for this one, if my wavelength is half, so if my wavelength goes down, okay. If my wavelength goes down, what do you think happens to the frequency? We just said it. Then it goes up. I'm just writing this backwards. The frequency has to go up then. So in our first example, for the frequency of the wave is double, the energy goes up. So if F goes up, then energy goes up. But if F goes up, wavelength goes down. They're inverse relationships. If wavelength goes down, then frequency goes up. They're inverse relationships. They do the opposite of each other. The very last question just says, what makes the different forms of electromagnetic radiation of light different? All we've been talking about for how they are different is just their size. That's it. All wavelengths of light are all energy. They all move at the speed of c. A lot of them come from stars that are emitting that energy out. So the only thing that is different between their colors and their energies is the size. The size of the wavelength. If they're really small, then they're fast. If they're really small, then they can get inside your body and corrupt your DNA. If it's a really big a really big wave, then it's just going to go right over you. It's not going to hurt you, and it's going to have to move slow. All right. So that is the end of notes. Y'all should be getting those turned into the box. I'm going to stop recording because that's all I needed recorded.